last video, or the last lesson really, was about temperature change and heat capacity. There is something else that happens, and it is phase change. So with phase change, what we've got is something very simple, right? We might have an ice cube melting. Melting into a puddle. That would be an example of a phase change because we start from solid and we end up in a liquid. And that happens at a particular temperature. For when we go solid to liquid, we call that melting. We call that when we go from a solid to a liquid, we need some kind of a heat exchange. So we add heat to this solid and it will become a liquid. We can keep adding more heat and it will become a gas. So somehow we need to be able to figure these out. Now if we're looking at water, this transition from solid to liquid happens at 0 degrees Celsius. If we're looking at something other than water, it'll be a different temperature. And from liquid to gas happens at 100 degrees Celsius. So what that means, if I were plotting the temperature of this thing, if I had a block of ice, I could have a temperature scale. Let's put it in degrees Celsius. And I'll go all the way across to here. So over here, I might have something. This is 0, and we'll put 100 up here. I might have this block of ice that starts out somewhere well below 0 degrees. I keep heating and heating and heating, and now I get to that 0 marker. Now what happens is the ice melts. While the ice is melting, the temperature is going to stay the same. So right here I have some heating. I have my super cold ice that's becoming regular cold ice. Over here I have the phase change. This is the melting part. Now that I'm all water, I can heat up, heat up, heat up again. So this is another heating phase. And then I'm evaporating. So this is my phase change. And once it's evaporated into steam, I can heat that steam up more. There is nothing saying that solid water, liquid water, and gaseous water have to have the same heat capacity, and they don't. That actually won't be the case for much of anything. So in between these red lines we have phase changes. Over here we are in our solid phase. In between these we are in our liquid phase. Then phase change, and then over here we are in a gaseous phase, which means that these phase changes happen at constant temperature, and that's an important thing. When we are doing these heating parts, we get equations that look like Q equals mc delta T. And they will have different C values, but it's the same process. During these phase changes, we would have a temperature change of 0. It's steady. So over here, what we have is we use something called latent heat. Which we give a capital letter L. Latent heat has units of joules per kilogram. And that's what's going on here. We're going to have a Q equals a mass times a latent heat. And over here, a Q equals a mass times the latent heat. Now we just need to talk about what these are. This one is going to have a latent heat of fusion. That's the one that deals with the phase change between solid and liquid. And this one's going to have a latent heat of vaporization. There are some compounds, some objects, I guess, that go straight from solid to gas. They don't do the liquid thing in between, and then you need a latent heat of sublimation. I'll write those out too. So if I'm going from solid to liquid, I call that melting, which you already knew. If I'm going liquid to solid, that one is freezing. If I go liquid to a gas, that one is evaporating, evaporation. And if I go gas to liquid, that one is condensation. If I go from solid straight to gas, which I get with something like dry ice, that one is sublimation. And if I go from gas straight to solid, which I get with frost, this is called deposition. Over here, the particular latent heat version that I want is a latent heat of fusion. For this one where I'm evaporating, I'm going to have a latent heat of vaporization. And where I am going straight from solid to gas or backwards, that's going to be a latent heat of sublimation. The formulas for these really are as straightforward as this. It's just Q is always going to be mass times the appropriate latent heat. And that's what we're doing with these. We are saying maybe how much heat does it take to get this block of ice to melt. So I have to do this in pieces. That is the one thing. If I have a block of ice at, let's say, -20 degrees Celsius, then let's see how that works. Maybe I want to take my ice at -20 degrees Celsius and I want to bring this up to steam at 150 degrees Celsius. Now I can't do this directly, but I can do this in pieces. I'm going to take my ice at -20. I'm going to heat this up to be ice at 0. Once I've done that, now I can take this to melt. So I would like this to be water at 0 degrees Celsius. Now I can heat up my water to the boiling point. I can now boil my water, but while it's boiling, my temperature is constant. And then I can heat it up to steam. So instead of doing this one step, to steam at 150, so instead of doing the one step, I'm going to have to do 5. But none of them are awful. This one is a temperature change. So this one's going to be a Q equals mc delta T. This one's a temperature change. That's a Q equals mc delta T. And this one's a temperature change. Q equals mc delta T. This one is melting. Q equals m times latent heat of fusion. and this one's evaporating. This is Q equals M times latent heat of vaporization. So I'm going to run through this with my numbers and just kind of do everything at once. Honestly, we don't need 2 videos for this. So I need some values. I'm going to need some specific heats, and I'm going to need some latent heats. Or rather, I'm going to need heat capacities and latent heats. Here we go. For the ice, I get 2090 joules per kilogram Kelvin. For water, liquid, I get 4186 joules per kilogram Kelvin. And for the steam, I get 2000. Joules per kilogram Kelvin. I would also like these latent heats, so let me find those. For water, I get a latent heat of fusion of 334, and this is actually in kilojoules per kilogram, and a latent heat of vaporization of 2260 kilojoules per kilogram. So now I have all the numbers that I need. I'm going to label these things, these steps, 1, 2, 3, 4, and 5. And I'm going to find the energy needed for each process. So for process 1, the one piece that I'm missing is how much mass. So let's go with 100 grams. I'm raising this from -20 to 0, so I'm raising this by 20 degrees. And I should get 4180. That's that first part. For step 2, I need to melt this ice. So I'm going to have Q equals M times latent heat of fusion. And these are tricky with the latent heats because they're often listed in kilojoules. So I just want to be careful about that. 334 times 10 to the third joules per kilogram. So I get 334 times 10 to the second, which is 33400 joules. Next, step 3. Step 3 is another heating. So I'll do that. I've got my 0.1 kilograms. I'm at regular water now, so 4186 joules per kilogram Kelvin. And I'm heating this from 0 to 100, so I'm heating this by 100. 100 times 0.1 is 10, times 4186 is 41860 joules. There's my step 3. Step 4, I am boiling this thing again. So Q is M times L vaporization. I get my 0.1 kilograms times my 2260 times 10 to the third joules per kilogram equals 2260 times 10 to the second, because that's what the 0.1 does. So 2260 with 2 zeros joules. Last one, 2000 joules per kilogram Kelvin. I'm just heating it up. 2000 joules per kilogram Kelvin, and I'm heating this from a temperature of 100 degrees Celsius up to 150. So I'm heating it up 50 degrees. And that works out to be 10,000 joules. So my whole process, all I have to do is add these up. I have a 4180 plus a 33400 plus a 41860 plus 6000 plus 10,000. And altogether that works out to be 315,440 joules for the whole process. None of them were particularly arduous pieces. It was a lot of small bite-sized pieces, and we are just figuring out how to put them together. That's bringing heat into phase changes.